Good morning, students. Today we are going to discuss about self-induction. Okay, students. In last class we discussed eddy current and their applications. Okay, students. So followed by the topic. Now we are going to discuss about self-induction. Okay, students. Yes. See this self-induction. Right. See this first one. When an electric current is passed through an insulated conducting wire, right, it gives rise to a magnetic field in the coil. Okay, so basically, when an electric current is passed through an insulated conducting coil, it gives rise to a magnetic field in the coil. Okay, so current flow to the coil, around the coil magnetic field is produced. Okay, right. Okay, so that the coil itself behaves like a magnet. So the coil act as a magnet that time. Okay, now see the second point. The magnetic flux produced by the current in the coil is linked with the coil itself. Okay, the magnetic flux produced by the current in the coil is linked with the coil itself. Okay, right. See this types of inductor coil. Types of inductor coil. See this is the insulated copper coil and this is a toroid. Yes, this is also coil, right, and this is also solenoid. So these are the types of inductor coils. These are the type of inductor coils. So when the current flow to the coil, around the coil magnetic field is produced. That time it is act as a magnet. Okay, students, right. Now come to the self induction. Right, now what is self induction? See this. As the strength of the current in the coil is changed, again the strength of the current in the coil is changed, the flux linked with the coil also changes. So if the current changes, flux also changes. Okay, right. Under such circumstances, an EMF is induced in the coil too. So induced EMF is produced, right? Okay, such EMF is called as a self-induced EMF. The EMF, self-induced EMF, and this phenomenon is known as self-induction. Which induction? Self-induction, right? So this is the very simple definition for self-induction. Okay, students, right. Now see this. To produce self-induction setup, so take a battery and yes, positive is connected to key, and negative another end is connected to the rheostat, and rheostat another end is connected to the one end of the conducting coil, and another end is connected to the negative of the battery. So conducting coil, wire, and was rheostat, key, and switch, right. So with the help of this apparatus we can produce the self induction, right. Okay, okay, students, right. Now see this, the circuit diagram. So this is the coil is connected to the rheostat and the battery. Okay, so one end is connected to positive terminal of the battery, another end is connected to negative terminal. So what will happen? I said no, when the current flow to the coil, around the coil what is produced? Magnetic field. So therefore these lines are magnetic field lines, right. Therefore come to this one. When current flow in anti-clockwise direction, that time that side is, it is act as which pole? Yes, north pole, right. So it is act as a magnet now, so that side have which pole? North pole. The same way, if you go to the another side, the current flows in clockwise direction, that side it is act as a which pole? South pole. Okay students, because the magnet has north pole south pole, no, therefore if the current flow to the coil in anti-clockwise direction, that side north pole, and if current flow to the coil in clockwise direction, that side act as a south pole. Okay students, right? Have any doubt? Okay, now yes, with the help of that yes circuit, small explanation. See this, if the number of turns in a coil is n and flux linked with each turn is pi, so flux is always pi, right? Then the total flux linked with the coil is n into pi, because n is the number of turns of the coil, no, that's why n into pi, right? Okay, in this case the total flux linked with the coil, total flux linked with the coil is directly proportional to the current flowing through the coil, right? Because current flowing to the coil, no, that's why the total flux linked with the coil is directly proportional to the current flowing through the coil. So therefore total flux is n pi is equal to L into I. So why sir here new one introduced? L is a proportionality constant and I is the current. Yes, that means Ni is directly proportional to I. Yes, directly proportional to I. If you remove the directly proportional, we have to use some constant. No, that constant is nothing but here L. L is the proportionality constant L. Yes, and L is called as self-induction of the coil. Therefore n pi is equal to Li. If this Li come to this side, n pi divided by I, right? Okay, see this, therefore the self-induction L is measure of the flux linked with the coil per unit current. Which current? Per unit current. Okay students, right? Now see this, the self-induction L or self-inductance L of a coil depends upon, yes, three factors. One more question, the size and shape of the coil. So the self-inductance depends on size and shape of the coil, and the second one is the number of turns of the coil, and the third one is the magnetic property of the medium within the coil in which the flux exists, right? And the self-inductance L does not depend on current. Self-inductance. Okay students, these are the 1 marks. Okay, right? Yes. Now continuation from previous this one. Okay, see this, differentiating n pi is equal to L with respect to time, I can get n d pi by dt is equal to L di by dt, right? Therefore in the case of self-induction, Faraday's law and Lenz's law holds good, right? Because Faraday's law also explained the induced EMF, and Lenz also to explain the direction of induced current. Therefore here Faraday's and Lenz laws holds good. Therefore hence the self-induced EMF in the coil is E. E is the EMF, self EMF is equal to minus n d pi by dt, right? D pi by dt. So this side is nothing but what? Yes, EMF. The self-induced EMF is also called back EMF. Which EMF? Back EMF. Okay students, right? Okay, yes, from the previous equation, which equation? See this one, I'm taking E is equal to minus L, because minus is current direction, so L di by dt. Therefore according to self-induction, L this side is equal to minus E divided by di divided by dt, right? Okay, now see this, the self-induction or self-induced EMF produced per unit rate of change of current in the circuits called self-inductance of the circuit, self-inductance of the circuit. Okay, and the unit of L is equal to unit of EMF per unit rate of change of current. Therefore A by S is equal to Vs divided by A, or otherwise the unit of self-induction is Henry. So commonly we used the unit of self-induction is Henry. Okay students, okay, right? Now yes, in our book this is the self-induction diagram. See, this is the coil, the end of the coil is connected to the battery in positive negative through the resistance, right? This is the magnetic field is present, this is the current. Okay, so when the current flow to the coil, around that magnetic field is present, right? Okay students, now yes, in our book, so this is the definition: an electric current flowing through a coil will set up a magnetic field around it. Therefore, the magnetic flux of the magnetic field is linked with that coil itself, right? If this flux is changed by changing the current, an EMF is induced in that the same coil, right? So this flux is changed by changing the current, and EMF is induced in that same coil. This phenomenon is known as self-induction, and the EMF induced is called self-induced EMF, right? Okay students, this is the book definition. Okay, now is derivation part. So this is that is for understanding purpose. When you increase the current, see this induced EMF like this, and if you the current changed, okay, if you are increase the current like this, and we are decreasing current like this, okay, when you are connected positive negative oppositely, if you change the direction of the current, okay, the induced EMF also changes. Okay, now yes, the definition, yes, I showed no that yes, Ni, that and all, yes, so please listen. So this is the book back derivation I simplified. Okay, self-induction, we know the definition of self-induction. What is self-induction? The magnetic flux change in the coil, yes, by changing the current. What is induced? EMF is induced. The same way here in self-induction, pi b is the magnetic flux linked with the coil, yes, and each turn of the coil, and n is the number of turns. Okay, therefore the total magnetic flux linked with the coil is n into pi. I said no, therefore according to the yes, which one, self-induction, the total magnetic flux is directly proportional to the current, therefore the current is I. If you remove the directly proportional, I have to use some constant, that is proportionality constant L. Therefore n pi by pi b, which is equal to L into I. If I am taking L this side, n pi b divided by I. Okay, so therefore this is equation number 1. If I am taking the current is flowing to the circuit is flowing to the coil is 1 ampere, what will happen? N pi divided by 1 no, therefore L, which is equal to n into pi b. L is the self-induction. L is nothing but what? Self-induction. Okay students, right? Now continuation. When the current I changes with respect to time, so when the current changes, what is induced? EMF induced, no. Therefore when the current changes with time, an EMF is induced. Therefore EMF is E, which is equal to minus, right, d n pi by divided by dt, right? n pi by divided by dt. So this is the total magnetic flux, right? Here, yes, this minus is that to oppose that, which one? Current flowing. That's why minus d n pi by divided by dt, right? So this n pi according to which one is self-induction? N pi is equal to L, no? That's why I'm taking, yes, n pi is nothing but L. Therefore, minus d divided by dt into L into I, right? Therefore, if this L come to this side, minus L di by dt, right? If this di by dt I'm taking 1 ampere per second, yes, the rate of, yes, change of current, the rate of flow of current in the coil is 1 ampere per second. What will happen? L into 1 L, no? Therefore, this L come to this side, what will come? Minus E divided by di by dt. If this di by dt taken as 1, what will happen? L is equal to minus E. That means the self induction is numerically equal to the which one? EMF. Okay, almost numerically equal to the what? EMF, induced EMF in the coil. Okay students, this is the derivation for the self induction. You understand the students? Shall I go to the next topic? Right, and the next topic is self induction of a long solenoid. Before that, in our book, this is the unit of inductance. So from this area 1 marks will come, so please listen. See, inductance is a scalar and its unit is Weber, yes, Weber per ampere, yes, or voltage second per ampere, right? It is also measured in Henry, so therefore unit of inductance is Henry. Here 1 Henry is equal to 1 Weber per ampere is equal to 1 voltage second per ampere. Therefore, the dimensional formula for the inductance is m L square t power minus 2 a power minus 2. So this is the important 1 mark. Okay students, right? Next, if suppose I am taking current is 1 ampere and n pi total flux is equal to 1 Weber turns, then the self induction L is equal to 1 Henry. Therefore, the inductance of the coil is said to be 1 Henry if a current of 1 ampere produce unit flux linkage in the coil. So this is the, yes, definition of 1 Henry. So please yes, underline. Okay students, right? If di by dt I am taking 1 ampere per second, then the EMF is equal to minus 1 voltage, then the, yes, self inductance L is equal to 1 Henry. Yes, therefore the inductance of the coil is 1 Henry. Sorry, this is the definition of 1 Henry, not this one. Okay, come to this one. The inductance of the coil is 1 Henry if a current changing at the rate of 1 ampere per second induced an opposing EMF of 1 voltage in it. Okay students, right? This is the 1 Henry definition. Okay students, okay, right. Now come to the self induction of a long solenoid, right? We know the self induction, no? L is equal to minus C. Here self inductance. Okay, see this. Consider a long solenoid of L, that is long solenoid of length L and cross sectional area A, and let N be the number of turns per unit length of a solenoid, right? And when an electric current I is passed through the solenoid, okay, a magnetic field is produced by it which is almost uniform and is directed along the axis of the solenoid. Okay students, so we are taking a solenoid with length L and area of fraction N, and number is the number of turns per unit length. Okay, right? And inside that the magnetic field is present. Okay, so when the electric current passes through the solenoid, magnetic field is produced around that. Okay students, right? Now see this self-inductance of a long solenoid. See, it has area of cross section, it has magnetic field, it has n number of turns, the length of the solenoid is L. When the current flow to the solenoid, around that what is produced? Magnetic field is produced. Okay students, right? Okay, yes, the theoretical. See this, magnetic field is produced, no, from that one. See this, the magnetic field at any point inside the solenoid, because current flowing to the solenoid, magnetic is produced, no, therefore the magnetic field B is equal to mu naught Ni. Mu naught is that what? Permeability in free space, right? Mu naught Ni. This is equation number 1. Now the magnetic flux passing through each turn, the magnetic field is also present, no, that's why the magnetic flux passes through the each turn. So what is the magnetic flux formula? We know that, yes, pi b which is equal to integral b into dA. So here A taken as area of fraction, entire area. Okay, therefore BA cos theta. This is a magnetic formula, no? Yes, and theta is taken as 0 degrees, so cos 0 is equal to 1. Therefore the magnetic flux is B into A. So this is equation number 1. Now this equation number 1 substituting in equation number 2, you will get pi b which is equal to B into A. That means mu naught, see that B value substituting in here, mu naught Ni into A, right? So this is equation number 3. Okay students, so this is magnetic field and the flux. This magnetic field substituting in this equation, you will get this equation. Okay students, right? And now come to the total magnetic flux. See this, the total magnetic flux linked with the solenoid, N is equal to N into L. Yes, number of turns per unit length, no, that's why N is equal to NL. Therefore N pi which is equal to, right, so this is N into is pi A. So what is N into pi by pi b, no, yes, Ns is equal to what? NL. Okay, what is pi b? Pi b is here, see that mu naught Nia, no, that one. So the third equation I'm substituting here. So N into pi b is equal to N is N value into mu naught Ni into A. Therefore N into N, N square. Therefore mu naught N square L into I into A. This is equation number 4. Okay, now according to self-induction, yes, self-induction, N pi by pi b which is equal to L into I. L is the self-inductance, right? Therefore N pi b which is equal to Li. Yes, therefore equation comparing the 4 and 5th equation, see that I am taking this is also N pi, this is also N pi. Therefore Li which is equal to mu naught N square Lia. Therefore here what will cancel? Ia cancel. Therefore L which is equal to mu naught N square A into L. So this is what? Self-induction, right? This is the self-inductance. Therefore this is even taken as number 6. Okay, right. And continuation, suppose if any medium present inside the solenoid, so therefore what is the self-inductance? L which is equal to mu is the permeability in medium, that's why here instead of mu naught I am substituting here mu. Therefore mu N square A into L. This is equation number 7. Suppose the solenoid attached with a dielectric medium, or the dielectric medium present inside the solenoid. What will happen? What is the self-induction? Right? What is the self-induction? L. Yes, which is equal to, yes, is equal to what is dielectric medium with the help of this relation mu naught, which is equal to mu divided by mu r. So if I am taking mu medium, mu naught into mu r, yes, therefore mu, instead of mu I am substituting mu r into mu naught, therefore L which is equal to mu naught into mu r, L square A into L. Mu r is nothing but relative permeability. Okay students, right? Okay, so this is that self-inductance of a long solenoid. Okay students, okay, right. So followed by this, energy stored in an inductor. Energy stored in an inductor. So inductor coil, no, that's why. See this, whenever a current is established in the circuit, the inductance opposes the growth of the current, right? In order to establish a current in the circuit, work is done against this opposition by some external agencies, and this work done is stored as magnetic potential energy. So here the work done is stored as magnetic potential energy. Okay students, right? Now come to that derivation part. See this, the inductor effect alone you are taking, therefore yes, when the current flow to the coil induced EMF at that instant time I am taking. So what is induced EMF? E is equal to minus L di by dt. We already know, right? So therefore E is equal to minus L di by dt. This is equation number 1, right? So please remember the current I is equal to rate of rate of flow of charge dq by dt. So the EMF is equal to minus L di by dt, right? Now work done is no, therefore dw work done, dw is the work done in moving a charge dq in the time dt against the opposition, yes. Therefore if I am taking dw which is equal to minus is opposition, E into dq, because dq amount of charge, no, that's why minus E, minus is the EMF and dq. Therefore from this current I am taking dq is equal to I into dt, therefore dw is equal to minus E I into dt. This is equation number 2. This is equation number what? 2. Okay, okay students, right? Okay, see this. So substituting E from S first equation, that is E value. What is E value? Minus L di by dt, no, that equation substituting in second equation. See this, dw is equal to minus, already minus value is there, therefore minus L di by dt into I into dt. So therefore minus into minus plus I, minus into minus plus L di by dt, yes, into I into dt. So what is cancel? Dt cancel, no, therefore dw is equal to L I into di, therefore this is the equation number 3. This is equation number 3. Okay students, yes, right. Now we have to calculate the total work done, therefore I am taking integral. See, the total work done is W is equal to integral of dw. So what is dw? Li into di, no, therefore integral 0 to I, this is the minimum current and this is the maximum current, therefore 0 to I Li into di. if I'm taking L outside, W is equal to L integral 0 to I into di. So this is that S formation of integral x into dx, which is equal to x squared divided by 2. Therefore, if I'm S integration, I can get I squared divided by 2, right? Therefore, L into I squared divided by 2 is limit 0 to I. Therefore, 1 by 2 outside, I can get W is equal to 1 by 2 L into I square. Yes, so therefore W is equal to 1 by 2 L into I square. This is equation number 4. Okay, students, this is equation number 4. Work done, right? Now, so this work done is stored as a magnetic potential energy. So which this is the work done now. Yes, see, this is the work done. W is equal to 1 by 2 Li square. This is the work done. So this work done only stored as magnetic potential energy. Therefore, magnetic potential energy is UB. B is the magnetic potential. Yes, so U is the energy, potential energy. Therefore, UB is equal to 1 by 2 Li square. Right? Okay. Now, this is equation number 5. And then the energy density, if I'm taking the per unit volume, if that energy is equal to UB is equal to UB divided by AL, because per unit volume, no, that's why I'm taking A into L, area into length. Therefore, see this, L is equal to mu naught N square into AL, right? Yes, UB value 1 by 2 L square, no, that's why that time that UB value substituting here, I can get Li square divided by 2AL. This capital L value here, therefore mu naught N square AL into I square divided by 2AL, right? Therefore, what is cancel? LL cancel and AA cancel. I can get mu naught N square I square divided by 2, right? Yes, in that magnetic field formula, in that coil, mu naught N into I. Therefore, yes, if I'm taking this square, mu naught square N square I square, but here N square is there and I square is there, only here mu naught. Therefore, and divide by mu naught, then only I can get the B square. Therefore, if this one simplified, B square divided by 2 mu naught. Therefore, mu UB is equal to B square divided by 2 mu naught. Okay, students, this is the derivation for the energy stored in inductor. So energy stored in inductor is the 3-mark question, and the self-induction inductance of the long solenoid is a 5-mark question. Okay, students, right? Okay, students, right? Today class is over. Okay, students, we'll see you on next video. Okay, students, thank you.